part 2 of simple linear regression, I'm talking about coefficient of determination first, and then some diagnostics we use to check the assumptions in our linear regression. Now, coefficient of determination is the squared correlation coefficient between the observed y values and the estimated or fitted values for the y or response variable. It tells us how well the regression line estimates or predicts the actual values. Or we can say that coefficient of determination is representing the proportion of variance of the response that can be explained by the model. Now, we compare the distance between each actual value to the mean with the distance between each fitted value to the mean of the observed values. So we say that r squared, this is the coefficient of determination, is the sum of the y hat I minus y bar square, which is the squared difference between the fitted value and the mean, divided by the squared distance between the observed value and the mean for the response variable. And here, this bit is called sum of the squared deviation of y. Okay, in a simple linear regression, we check a few assumptions, and it will be valid, this model will be valid only if these assumptions hold. One is the assumption of linearity. Linearity is, we say that the response variable y has a roughly linear relationship with the predictor variable x. So this assumption of linearity, we want to assume there's a linear relationship between x and y, can be checked by the scatter plot. Now we have to have another assumption, which is the errors are independent. And that is we talk about the homoscedasticity assumption, which it means that the error terms have got the constant variance. Error, you remember that it was the difference score between the observed value y and the fitted value y hat. Now, that error residuals should have constant variance. Now, that means for each value of x, the distribution of residuals has the same variance. This means that the level of error in the model is roughly the same regardless of the value of explanatory variable. The homoscedasticity assumption, it can be checked by residual versus fit plot. So there are a few plots that you have to go through in order to check the assumptions for linear regression. Now we have to check for outliers, because outliers have a very influential effect on your line of regression. One outlier can make a huge difference in the line of best fit. Now, the other assumption is residuals are normally distributed. So, residual plot can be used to ensure that there are no systematic biases in our model. Now, in the output for the R output that you will see, that is checked by QQ plot. Now, in regression analysis, we can raise the independent variable by an exponent or take its log to fit a curve and still have a linear regression. What do we mean? We have got X column and we have got Y column. We are investigating the relationship between X and Y. We are looking at simple linear regression. In here, we say that, okay, you scatter plot and you will see that the plot is a bit curved. So you say, okay, how about if I square the values of x and then get this scatter plot again? If you see that linearize your scatter plot, the relationship is more linear, then you can do simple linear regression between y and x squared or log of x. These are, we say that we are linearizing the our values in order to use simple linear regression. Now, because the model is still linear in the parameters, it is in the category of linear regression models. When we proceed with the linear regression and follow with diagnostics for regression analysis and observe violations in the assumptions of linearity condition, which by looking at residual plots, we would have to refer to the non-linear regression models that we are going to talk briefly about them later on. Okay, now let's talk a little bit about residuals versus fits. So it's a plot of residuals versus fit can be used for checking violations of linearity and the possibility of non-constant error variance. So there should be no obvious pattern or relationship between the residuals and fits. Non-linear patterns such as quadratic relationship could be an indication that the linear model is not appropriate. Now, the residuals should not appear to vary differently for different magnitudes of fits. If that was not the case, then it could indicate that the variance of the errors is related to the magnitude of the explanatory variable. So, just to illustrate this, here we have got residuals versus fitted values, and you can see that there's no pattern. All the dots are spreading across the zero line. So this is the assumption holds, the assumption of equal variance for residuals. But here you can see that the plot is just fan shape. So this is not homoscedasticity assumption is violated, so it is a heteroscedasticity in here. Can be observed. So it means that the residuals do not have constant variance because they will be getting further and further from the zero line. And here you can see that it's a non-linear relationship, and it is a little bit, we can say it's like a curvy linear relationship. These are all residuals versus fits plots. Okay, now to check the assumption of normally distributed residuals for linear regression, we use QQ plot. Now here you can see that here it says theoretical quantiles and here it says sample quantile. Now QQ plot or quantile plot is used to investigate whether a data set is distributed according to a specific distribution. For example, if we have a set of genes and we want to check whether the genes expressions for these are normally distributed, we can use normal QQ plot. Just be sure that this is just to tell you what is QQ plot. It has this bit, it has nothing to do with the linear regression. Or if we wanted to check whether these genes expressions were uniformly distributed, we use uniform QQ plot. If a set of observations is approximately normally distributed, the normal QQ plot will be approximately a straight line. One of the diagnostic checks for linear regression is the QQ plots of the residuals, which should produce an approximately a straight line. Okay, just a bit of explanation for that. We first order our standardized residuals and then plot them against the standard normal quantiles. So, for example, here we have 9 residuals. So we would have divided the standard normal distribution into 10 equal sections. So we have 0.1 quantile. It means that the point at which 10% of the data fall below and 90% of the data fall above that value. All right? So the theoretical quantile is in the x-axis. So this is the value corresponding to the 0.1 quantile or 10th percentile of a standard normal distribution if the data was divided into 10 equal sections. So here, we have got the sample quantile, which is observed values in our sample. So this value is the smallest standard normal residual corresponding to our sample. So these two values, when we put them the one dot, it will go here. Then we will do for the rest 9 dots we have, and then we see that if these dots fit to a straight line, then our QQ plot says that residuals are normally distributed. This is just for your understanding. When you go to your lab, you will see that you will have all these plots produced by your R programming, and then you just have to look at the plots and decide that the assumptions for linear regression holds or not. So again, a reminder of the assumptions that the regression model is linear in the coefficients and the error term. The error term is normally distributed from QQ plot, has a population mean of 0 and constant standard deviation from residual plot, and all independent variables are uncorrelated with the error term and with each other. Okay, so what if there was a violation of the linear regression assumptions? Then we try to linearize the relationship. It means that, as I said, transform the response and the predictor variables so that the relationship between the transformed variables is linear. If that did not work, then we have to do other techniques such as fitting polynomial regression out of the scope of this subject. That is when the power of the independent variable is more than 1, and or complex spline regression, again out of the scope of this subject. Split the data into sub-samples and fit polynomial regression in each part of sub-sample, making sure the line or the curve that fits a smooth curve. And at the end, we should fit a nonlinear function to the data, which nonlinear least squares NLS, which again, we are not going to teach it for this subject this time. Okay, and there is one more point. It is confidence intervals and prediction intervals for the response variable. When we estimate a regression model for a data set, we can generate two different intervals. The confidence interval is an interval estimate for the mean response, and the prediction interval is an interval estimate for a single future response. Thank you.